The electrons in an atom determine how it reacts with other atoms to form chemical compounds. Understanding the organization of electrons in the atom is absolutely key to understanding chemistry at the level of the atom. In this presentation, I will describe the electronic structure of the atom. In other words, I will describe how the electrons are organized around the nucleus of an atom. I will start with a simple but outdated model called the Bohr model. I will then introduce the modern quantum mechanical model, where the concept of orbitals and probability are important. I will discuss the different types of orbitals, how they are organized into shells and subshells, and how they fill with electrons. All of these things are captured by what is called an electron configuration, and I will describe how to write the electron configuration describing atoms of a particular element. The Bohr model is an early model of the structure of an atom. Here I draw a two-dimensional representation of the Bohr model for the lithium-7 atom. Remember that atoms aren't flat. The nucleus of 3 protons in blue and 4 neutrons in pink is orbited by electrons. These electrons organize themselves into shells, much like layers of an onion. The electrons are seen as particles that circle or orbit the nucleus, similar to a planet orbiting the sun. Each electron orbit is at a specific distance from the nucleus. In the case of the lithium atom, there are electrons in 2 different shells. The first one, which is closest to the nucleus, contains 2 electrons, and the second one contains lithium's 3rd electron. The Bohr model, and in particular viewing an electron as a particle circling the nucleus, can be very useful, but it is not entirely accurate. The realm of the very small, such as the atom, requires special considerations that are not apparent from our everyday surroundings as perceived with our normal senses. One consideration is known as wave-particle duality. Very small things, like the electron, move as much like a baseball as they do a wave in the ocean. At times, it is useful to think of them like a baseball. At other times, it is more useful to think of them like a wave that spreads out. Such considerations gave rise to the modern quantum mechanical model of the atom. The rest of this presentation is based on the quantum mechanical model, but for simplicity, I will at times speak of atoms in ways that are reminiscent of the Bohr model. In the quantum mechanical model of the atom, electrons don't have a position that we can track exactly. Instead, we talk about the electron like a diffuse cloud. We talk in terms of probabilities instead of definite locations. Consider taking a slice of an atom to reveal a thin section, much like the section you would get by slicing a thin piece of apple. The seeds in the center are analogous to the nucleons, and the flesh of the apple analogous to the electron cloud. The electron cloud for a real atom is defined in terms of probabilities. Here is a cross-section of an atom showing the probability of finding one of the many electrons in the atom sketched out in a contour map. At the center is the nucleus. The lines or contours on the plot define the electron cloud in terms of the probability that the electron will be in a particular location, defined by the coordinates x and y. The color indicates the probability. White is high probability, and blue is low probability. This is just like a relief or topo map of the Earth's surface, but where elevation is replaced by the probability of finding an electron. An alternate way of showing this same information is a 3-dimensional plot. This would show position x and y in the cross-section, with the third axis being the probability of finding an electron. From either representation, it is apparent that the electron has a high probability of being found on either side of the nucleus. We can draw a shape that conveys the information in this probability distribution. In this case, I draw something that looks a bit like a dumbbell or the symbol for infinity. There are 2 lobes within which it is most probable to find the electron. The electron clouds describing various electrons can have different shapes and sizes, and these electron clouds are called orbitals. An orbital can be thought of as a container for an electron having a particular size and shape. The dumbbell-shaped orbital that I just showed is called a p-orbital. It is just one of many possibilities. Orbitals come in many shapes and sizes. The orbitals are organized into shells and subshells. Here I draw a table of some of the possible orbitals organized by their shell number and subshell designation. The shell number can be any positive integer. Here I show the first three. For historical reasons, the subshell designation is specified using letters. The first four are S, P, D, and F. After F, the designations follow the order of the alphabet. The subshell designation gives the shape of the orbital. An orbital, given the S subshell designation, is shaped as a ball. It is spherical. An orbital is labeled using its shell and subshell designation. Here, 1, S. As the shell number increases going down the table, the average distance the electron is found from the nucleus increases. I represent this by drawing the orbital bigger. The electron in the 2s orbital is on average further from the nucleus than the 1s, and the 3s further still. After the s orbital comes the p orbital. The rules of quantum mechanics govern that there can only be as many subshell designations within a particular shell as the shell number. Hence, shell number 1 has only the s subshell. There is no 1p orbital. Shell number 2 has both s and p orbitals. Drawing the p orbital gives us two types of orbitals, s and p, in shell number 2, the 2s and the 2p. Shell number 3 has three subshell designations, s, p, and d, giving us the 3s, 3p, and 3d orbitals. Here we see for the first time the shape of a d orbital, which has four lobes. Remember, the number of subshells in a given shell is given by the shell number. Shell number 1 has one subshell, shell 2, two subshells, shell 3, three subshells, etc. The subshell designation starts at S, then P, then D, then F. After that, it follows the alphabet, G, H, I, etc. Summarizing the meaning of shell and subshell numbers, the shell number gives the size of an orbital. A larger shell number means the electron is on average further from the nucleus. As we go down the table, the orbitals get bigger. The subshell number gives the shape of the orbital. S orbitals are spherical, p orbitals are dumbbell-shaped, etc. The shell and subshell numbers provide an address that labels a particular orbital, much like a section and row designation on a ticket to a large arena. Analogous to the fact that there can be more than one seat in a row of a large stadium, each subshell can also have more than one orbital. For instance, the p subshell has three different p orbitals, each pointing in a different direction. In other words, each with a different orientation. The number of orbitals in a subshell increases by 2 with each subshell. The s subshell has one orbital. The p subshell has 3. The d subshell has 5, etc. Remember, the number goes up by 2 each time. Orbitals can be thought of as containers for electrons, which I represent here as a box. Each container can hold up to 2 electrons. Quantum mechanics tells us that each electron must have a unique designation, or a unique set of labels. This means that we need one more label beyond shell and subshell to distinguish between the 2 electrons in each container or orbital. The additional label comes from the concept of spin. Certain properties of electrons are like those of spinning tops. We can imagine 2 directions of the spin. Here, the spin of the top is clockwise, if viewed from the bottom. If the top is flipped over, then the spin will appear counterclockwise. 2 electrons in the same orbital differ by a quantum mechanical property known as spin. One of the electrons behaves like the upright spinning top and is called spin up. The other behaves like the upside down top and is called spin down. To show the electrons in the orbital, the box is filled with 2 arrows. one pointing upward, the spin-up electron, and one pointing downward, the spin-down electron. There are many more orbitals available to be filled than there are electrons in a typical atom. So which orbitals do electrons end up in? Consider, for instance, a neutral atom of iron. The atomic number of iron is 26, which tells us that the neutral atom has 26 electrons. Which orbitals do these electrons end up in? The most stable arrangement of electrons is called the ground state. In this state, the electrons fill up orbitals from the lowest energy orbital to the highest energy orbital. But what does high or low energy mean here? If the forces of nature act to move a particle from one place to another, the particle is moved from a position of high potential energy to one of low potential energy. For instance, if you are 10 feet in the air, gravity will pull you to the Earth's surface. In doing so, we say you go from having a high potential energy to a low potential energy. The forces of nature move you to the lower energy, more stable state. The energy of an electron in an orbital is determined by two things. The first is how close the electron in the orbital is to the nucleus. The closer, the lower in energy. This is because of the attraction of the negatively charged electron to the positively charged protons in the nucleus. Positive and negative charges attract one another through what is called the Coulomb force. The closer a positive and negative charge, the lower the energy. The second is interaction with other electrons. Two electrons, both having negative charge, will repel one another. The more an electron in a particular orbital interacts with its neighboring electrons, the higher in energy it will be, the less stable it will be. These two factors lead to the orbitals filling in the following order. Shell number 1, consisting of the 1s orbital, fills first because electrons in the first shell are closest to the nucleus. Electrons then fill the second shell, with the s subshell filling before the p subshell, because of the way the electrons added to these shells are repelled from one another. We then start the third shell, filling the 3s and 3p orbitals, but then there is a bit of a surprise. The 4s orbital in shell 4 fills before the 3d orbital in shell 3. Again, this is due to the nature of the interactions between the electrons in the various orbitals. The order up to now and beyond is captured by a simple mnemonic. First, make a table placing the orbitals of the same shell in the same row and orbitals of the same subshell designation in the same column. Then, starting at 1s, draw a diagonal line down and to the left. For each row the diagonal goes down, it goes to the left one column. Our first diagonal only goes through the 1s. That is the first orbital to fill. Now move the starting point over one column and draw another diagonal. This goes through the 2s, the next orbital filled. Moving over one more column, the diagonal goes through the next two orbitals to fill, the 2p and 3s. Continuing in the same pattern makes the 3p and 4s next, followed by the 3d, 4p, and 5s, then the 4d, 5p, and 6s. The pattern can be continued for as long as needed. We are almost ready to answer the question as to what orbitals the electrons in an atom occupy. The tabulation of this occupation is called the electron configuration. The mnemonic that was introduced on the left gives us the orbital filling order. We also need to know how many electrons each subshell can hold. There is one orientation of s orbital, so each s subshell has one orbital that can hold 2 electrons. There are 3 orientations of p orbitals, so each p subshell has 3 orbitals, which can hold 3 times 2 electrons per orbital, or 6 electrons. There are 5 orientations of d orbitals, so each d subshell can hold 5 times 2, or 10 electrons. There are 7 orientations of f orbitals, so each f subshell can hold 7 times 2 or 14 electrons. Note that because the number of orbitals goes up by 2 with the subshell designation, and because each orbital can hold 2 electrons, the number of electrons in each subshell goes up by 4. As we will see, in filling orbitals of a particular subshell, electrons fill singly before pairing up. Now we can write the electron configurations of various atoms. These configurations are lists that give the number of electrons in the orbitals for each shell-subshell pairing. We start with hydrogen. What is the electron configuration of hydrogen? The hydrogen atom has 1 electron. The first orbital to be filled is the 1s orbital. I draw this pictorially, representing the 1s orbital as a line, and drawing an arrow above it to represent the electron. The electron configuration is then written as 1s superscript 1. The superscript shows the number of electrons in a particular shell-subshell pairing, in this case 1. The electron configuration is said to be 1s1. What is the electron configuration of carbon? Carbon has 6 electrons. The first 2 go into the 1s orbital, 1 spin up and 1 spin down. Remember, the electrons in a particular orbital must have different spins, as represented by the direction the arrow is pointing. Following the path set forth by the mnemonic device on the lower left, the next go into the 2s orbital. There are 2 electrons remaining to go into the 3 p orbitals in shell 2, which are next in line. Electrons go into orbitals of the same subshell singly before pairing up. So the 2 electrons are shown in 2 different p orbitals. The lines and arrows I have drawn are a longhand way of writing the electron configuration. The notation showing only the total number of electrons in each subshell is a more compact way to write the electron configuration. For this shorter notation, I first write 1s to symbolize the 1s subshell, which only contains the single 1s orbital. Counting the arrows, we see that there are 2 electrons in this subshell, which is indicated by a superscript 2. Next, I write 2s to symbolize the 2s subshell, in which there are also 2 electrons. Finally, I write 2p to symbolize the entire 2p subshell, consisting of 3 2p orbitals. There are 2 electrons in this subshell, so I add a superscript 2. What is the electron configuration of titanium? Titanium has 22 electrons. We again follow the order of orbital filling we have established. 2 electrons in the 1s orbital, 2 in the 2s orbital, 6 total in the 3 2p orbitals, first put in singly and then paired, 2 in the 3s orbital, 6 total in the 3 3p orbitals, and then the filling table tells us that the 4s orbital is next, which occupies 2 more electrons. This leaves us with 2 more electrons. Each singly occupies one of the 5 3d orbitals. Writing the total number of electrons in each subshell, the electron configuration is then 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Returning to our original question about iron, you should now be able to write its electron configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. To summarize, I will use a Bohr-like picture to illustrate the organization of the orbitals into shells and subshells. Remember, electrons really don't occupy orbits like planets orbiting the Sun, but the orbitals are organized into shells that increase in size or distance from the nucleus as the shell number goes up. Each shell is broken into a number of subshells given by the shell number. First, I draw the nucleus of the atom. The 1s subshell in shell 1 is closest to the nucleus, so I draw its orbit near the nucleus. Electrons in shell 2 are an average further away, and because the shell number is 2, I draw 2 subshells, 2s and 2p. Electrons in the third shell are further still, and shell 3 has 3 subshells, 3s, 3p, and 3d. Finally, I draw the fourth shell with its 4 subshells, 4s, 4p, 4d, and 4f. I use a box to represent each orbital within a subshell. A subshell with the s orbital designation has 1 orbital, so I draw 1 box for the 1s orbital. As with any orbital, it can contain 2 electrons of different spin, one drawn spin up and the other spin down. Similarly, the 2s subshell has 1 orbital. The p designation of the 2p subshell means it has 3 orbitals. I fill these keeping in mind that orbitals of a particular subshell fill singly before pairing up. The 3s subshell has 1 orbital. The 3p subshell has 3 orbitals. It seems logical to next fill the 3d orbital. But remember, our orbital filling order tells us that the 4s orbital fills before the 3d orbital because of the way the electrons interact with each other in these orbitals. The distance from the nucleus is not the only thing that determines the energy or stability of the electron. Hence, I draw the single 4s orbital next and fill it with 2 electrons before coming back to the 3d orbital. The d designation indicates that there are 5 orbitals in the 3d subshell. I fill them first singly and then pair. One can continue in this way up to the number of electrons the atom contains. If I stop here, I've used 30 electrons and have a representation of the electronic configuration of zinc. The shorthand for this would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10.